Today, we're diving into advanced video tracking with ProTracker. Imagine tracking any point in a video with precision, even if it disappears or blends into the background. ProTracker uses a clever probabilistic approach to fuse optical flow and long-term features, making it robust against challenges like occlusion and motion blur. Whether it's following a cyclist or tracking a goat's hooves, it always shines with smooth, reliable results over extended durations. Let's dive in!
Let's start by looking at how this research tackles point tracking in complex visual scenes. Notice the images here. They feature dynamic scenarios, like athletes jumping, skateboarding, and busy city streets. These examples show how challenging it can be to accurately handle motion and structure together. So what's the main idea? The authors propose a method that combines both geometry and motion into one probabilistic framework. This is different from older tracking methods that can get confused by occlusions or big changes in viewpoint. Here, they address those problems by making predictions about where points should be, then updating those predictions with what they actually observe. That way, they reconstruct object motion trajectories with solid precision, even when the environment is cluttered or constantly changing. Take a look at the colorful lines over real-world actions. Those lines represent the tracked motion trajectories. They show how the model can capture detailed, real-time movements in a variety of settings. By blending spatial and temporal information, this technique remains robust and scalable, opening new doors for applications like augmented reality or motion capture in tough conditions. Now let's consider the abstract and introduction. The paper introduces a new approach for point tracking in videos that emphasizes long-term accuracy. How do they pull it off? They fuse optical flow with semantic features using a probabilistic integration scheme. In simpler terms, they look at both the way objects move from frame to frame and the meaning of the objects, their semantic features. Then, they smooth the trajectories by picking the most reliable predictions. The authors also mention a clever way to handle occlusions. Points that disappear for a while can be relocalized later by using feature correspondences that track them in the long run. This ensures continuous trajectories without gaps. They've tested this method on different benchmarks and found it works well across unsupervised, self-supervised, and supervised setups. Extensive experiments back up the system's performance, and they plan to release the code online. In the introduction, the emphasis is on long-term dense tracking, meaning every pixel is followed across video frames. Traditional supervised methods can fail when the test data is very different from the training data. Some existing approaches also don't fully exploit temporal dynamics, which reduces robustness in complicated scenes. That's what inspired this more flexible and resilient tracking system. Moving on, the next section discusses the obstacles in point tracking, especially over long periods. One issue is how to handle objects that leave the scene or get blocked by other objects. Some methods try mapping everything to a single 3D space for consistency, but that can blur the fine details of motion. Others, such as DynoTracker, rely on semantic features and can still stumble when the features overlap or get ambiguous. So what's the proposed fix? The authors introduce a probabilistic integration framework inspired by Kalman filters. In essence, they combine optical flow with long-term correspondences and refine those inputs. They first remove noisy predictions to prevent them from causing more errors later. Then, they use a hybrid filter that taps into geometry and object-level features, making everything more robust. The end result is that uncertainties in the motion are balanced with confidence levels, which leads to smoother and more reliable tracking paths. In the related work, they review optical flow methods. These focus on motion between consecutive frames, but can struggle with bigger movements or biases in training data. For tracking over the long run, you often need to add extra components to cope with those shortcomings. Continuing the discussion on challenges, this section shows how the authors tackle missing segments in trajectories by blending optical flow with a special, long-term feature correspondence model. Optical flow is great for short-term motion, but it fails if an object vanishes and then reappears. That's where those long-term correspondences step in, helping fill in the blanks and cutting down on drift over time. There's also a note about dense correspondence methods. These methods compare pairs of pixels across frames to find matches. Modern foundation models provide robust features, but they may be lower in resolution, so precise tracking can suffer. They're still handy for filtering out mistakes, but aren't enough for fine-grained accuracy on their own. Tracking any point in the scene is the ultimate goal. Recent approaches such as TAPNet and ProTracker use spatial and temporal context, often with supervised training. Here, the authors improve on those methods by combining probabilistic integration with these long-term feature correspondences. Next up, take a look at the diagram in this section. It breaks down the proposed pipeline into 4 major steps. First, there's sample and chain, where the system picks key points and uses optical flow to link them over frames, giving an initial guess for each trajectory. Second, there's long-term correspondence, which is all about relocalizing these points across bigger time gaps. Even if they disappear, this step uses feature matching to bring them back on track. Then we get to the hybrid filter. This part applies masks and feature filters to get rid of noisy data, leaving behind cleaner trajectory candidates. Finally, probabilistic integration brings it all together by merging filtered predictions with the long-term correspondences. This last step creates smoother motion trajectories, using both short-term optical flow and long-term cues. Overall, these 4 steps work as a solid framework to handle difficult tracking scenarios, including occlusions and drift. Now, if you look at the details here, you'll see how the authors track a point across video frames, even under serious challenges like objects blocking each other. The pipeline begins with rough guesses about where the points will go, based on both optical flow and those long-term correspondences. Then, there's a hybrid filter with 2 parts. The first part is an object-level segmentation model that acts like a gatekeeper, filtering out points that belong to irrelevant objects. The second part is a geometry-aware feature extractor, making sure that only points that match the original point's appearance get through. By combining these two, the filter avoids unreliable predictions and narrows down any confusion in regions that look similar. Once that's done, they use probabilistic techniques to integrate the filtered predictions over time. This enables stable tracking, even when the scenes are really busy or when occlusions persist. Moving ahead, we see how long-term correspondences and bidirectional flow integration improve accuracy. You might ask, what if a point vanishes and then reappears? Well, that's exactly where these long-term correspondences come in. They relocate the missing points in a keyframe so the model can pick up where it left off. After that, forward and backward integration refine the motion prediction. Look at the figure here. It shows long-term key points anchoring the tracking, while integration smooths out shifts from one frame to another. The probabilistic flow integration takes multiple predictions, like forward flow, backward flow, and merges them statistically. This helps cut down errors and makes the whole system more robust, even in tough scenarios where objects overlap or move unpredictably. Next, the authors talk about the probabilistic integration method, inspired by the Kalman filter. They treat each flow prediction as a Gaussian distribution, with a mean and variance. By combining these distributions, they refine the predicted location of each point in the next frame. If one prediction is much more confident than another, it gets a higher weight. This process continues frame by frame, gradually updating the point's estimated position. It also accounts for how much each frame's prediction aligns with the others. They use a constant factor to handle correlations between frames, so if the motion is consistent over a span of time, the model trusts it more. This approach boosts both accuracy and reliability in trajectory tracking. Here, the discussion moves into how these probabilistic ideas further refine tracking. First, the algorithm combines predictions and confidence scores from multiple previous frames. The more reliable a prediction is, the more weight it carries. If no valid prediction can be found, the point is marked as occluded until something changes. After running forward through all the frames, a backward pass picks up points that might have been lost. That means starting from the end of the sequence and moving in reverse, which helps recover missed or occluded targets. They also restrict the process to high-confidence key points and use similarity checks for extra validation. All this ensures that the system maintains robust tracking, even when scenes become very complicated. In this part, you'll see how long-term correspondences are merged into flow-based systems. Why does that matter? Because it reduces the drifting errors that often occur in long videos. If a point pops back into view, these correspondences help match it to its earlier position. The authors use a feature extractor and heat map refiner, trained on pre-computed optical flow plus another signal, to find key points that matter most. These key points realign the flow predictions, so reappearing objects stay locked in place. Check out the experiments on real-world datasets like Davis currents. There are two modes, query first and query strided, which evaluate different aspects of the tracking. The method seems to handle complex motions well, maintaining continuity and smoothness across a range of scenarios. Now let's see some visual results. Look at the images showing dense point tracking across challenging scenes. At the top, we have the query images, which are the initial frames used for comparison. Below, you'll find the outputs from various methods like ProTracker, SPA-tracker, and LocoTrack. Each row gives us a glimpse of how these methods handle motion and occlusions. Notice how ProTracker, the proposed system, shows trajectories that remain accurate and continuous in busy or dynamic areas. The dense colored lines you see represent the motion of tracked points. ProTracker's paths appear smoother and less broken than the others, which highlights its ability to keep following points over time. This section offers a more direct comparison of ProTracker against methods like CoTracker, Spatial Tracker, LocoTrack, TAP-TR, and self-supervised models such as CADEX++ and DinoTracker. They use scenes from TapVid Davis, including a person with a bicycle and a goat in a rocky background. Each row shows how well each method handles tricky situations like overlapping motion or partial occlusions. Have a look at ProTracker's results. They remain more consistent across frames and better manage the complexities of the moving scene. Everything is displayed in a 256 by 256 resolution for fair comparison, but the original resolution is also provided if you want a closer look at those details. Next, check out the performance comparison. There are two tables summarizing how ProTracker fares compared to other methods, both supervised and unsupervised. The metrics include average displacement error, overlap accuracy, and alignment accuracy. Across the board, ProTracker scores the highest. In the first table, it beats the best self-supervised methods, and in the second, it also surpasses supervised ones. They specifically mention challenging datasets like kinetics first, where ProTracker shows that it can track points accurately under conditions that involve both object and camera movement. The numbers in these tables highlight the improvements, so be sure to take a look. The authors also describe the kinetics dataset, which has over 1,000 videos, each with 250 frames. It focuses on human activities that include object motion and camera movement. They selected a set of 100 videos for evaluation. Then they used metrics from the TAP-VID benchmark, such as visible point tracking accuracy and occlusion accuracy. Visible point tracking checks how well the points stay within certain pixel error bounds, and occlusion accuracy evaluates how well the system predicts when points are blocked. There's also an average Jacquard metric, which balances correct predictions versus false ones. These metrics together ensure a thorough assessment of how each method handles complicated visibility issues. Now let's look at the qualitative and quantitative evaluations. Think of sequences like bike packing, where the system continuously tracks points on the person rather than the bike or the background, or the goat sequence, where multiple hooves can overlap. Here, the method stays on the right points, even when things get messy. Several elements make this happen. Dual-stage filters prevent drifting, long-term key points provide re-identification when an object re-enters the scene, and probabilistic integration smooths out the movement. If you check out the table here, you'll see the ablation results. What happens if they remove certain components like key points or probabilistic integration? The performance changes, showing how important each part is for both accuracy and robustness. Finally, the paper discusses how they systematically tested each component in an ablation study. Removing long-term key points caused a big dip in performance because they help recover lost trajectories during occlusions. Without geometry-aware features, the model can get confused by look-alike regions. Meanwhile, mask filtering reduces errors from optical flow, which bumps up the reliability of the entire pipeline. The probabilistic integration is crucial for refining uncertain predictions. They end by noting that the method effectively handles occlusions, complex motions, and long time gaps. A limitation is that they still rely on test time training for key point extraction, but future improvements in feature extraction might allow completely unsupervised tracking in real time. That wraps up the deep dive today. Thanks for joining us.